Hi everyone, Happy New Year and thanks for coming out. My team and I are very excited to share Haven with you today. Haven is an open source solution for easily and securely managing your application secrets. It abstracts away the complexity and overhead of secrets management for software engineers so they can get back to development without compromising security. Before we talk more about Haven, we'll build some context around that complexity and overhead itself. We'll wrap up your knowledge about secrets, why you should handle them properly, and what can happen if you don't. Then we'll cover best practices and existing solutions that can help you in this space. And last but not least, we'll introduce you to Haven and you'll see where it fits into the picture. So let's dive right into it. First, you might be wondering to yourself, what is a secret? A secret is something you want to keep secret. More specifically, it's a sensitive piece of data that authenticates or authorizes you to a system. For example, you may have a connection string that you pass to a database, so you can authenticate a session and request data from it. Or you may have an API token that you supply when you make a call to your cloud provider, so you can read and write from its storage. And you may have a private key related to a TLS certificate that you present to your clients, so you can authorize yourself into an elevated position of trust. Each of these things is a secret because they are in and of themselves some mechanism of access. If your database password falls into the wrong person's hands, it can be used to authenticate or authorize that person to perform dangerous actions they shouldn't. So at least in the context of your application, that's a secret, and you don't want it to leak. Before we go on, we should clarify what a secret isn't. You probably have other sensitive data you'd like to keep secret too, like credit card or protected health information, but they're not secrets if they don't directly authenticate or authorize you to a system. Yes, a credit card number matters, and yes, it should be stored securely if you're storing it for whatever reason, but it's not in scope when we talk about application secrets. However, you can add a layer of protection over it by protecting your application secrets in the first place, such as database passwords. Secrets are often confused with configuration too. Configuration is important because it influences how your application operates, but not all of it is really private. Let's say your configuration defines parameters for a database connection, like an adapter and a password. We already mentioned why we have to keep the password secret, but it's not so critical to keep the adapter secret too. While it connects your application to the database, it doesn't authenticate or authorize you in any way, and your data won't be compromised if it were to leak. So in that sense, it's not a secret. Now, hopefully that gives you a hint about why things that are secrets are important. After all, they're called secrets for good reason. The principle of least privilege states that any user, developer, program, or process interacting with your application should only have access to the things they need to perform their function, the absolute bare minimum. Let's pause for a moment then and ask, if someone has just a bit more access than they really need, or one or two secrets happen to leak here or there, what's the risk? According to the principle of least privilege, anyone working on your application should only have access to the secrets necessary for their work. But maybe you don't want to bother controlling access to your secrets. You're on a small team, you know everyone personally, you trust their intentions. However, people make mistakes. Overprivileging developers and giving them access to secrets they shouldn't have access to can lead to honest but costly mistakes. For example, in 2017, DigitalOcean had an outage due to their primary database being deleted. The root cause was a developer misconfiguring automated testing with production credentials. As a result, DigitalOcean announced they would have to drastically reduce access to the primary system. Now, even if developers could be picture perfect, security wouldn't be such a grave concern if there weren't bad actors out there. Mishandling your secrets can give attackers the wrongful ability to elevate themselves into positions of trust where they can do great harm. And this can be very costly where customer data is concerned. For example, you may remember Capital One making headlines in 2019 when they had a data breach that affected over 100 million individuals. That was due to a vulnerability around configuration secrets involving AWS S3 buckets. The attacker previously worked as a developer for AWS and was able to exploit a misconfigured firewall to extract files in a Capital One directory stored on AWS servers. In fact, the misconfigured firewall had too many permissions. It could list and read any file in any bucket of data when it shouldn't have been able to. And still, data can be compromised even without human error or malicious intent. Data can be leaked via third parties that simply don't understand your secrets are sensitive and how to handle them with care. That's because they shouldn't have had access to them anyway, and it's hard to say what they'll do with that unintended access. It can take just one leaked secret to unlock more secrets or very important sensitive data, compounding any data leak. So not only do you break the principle of least privilege, you also break the principle of least astonishment, in that your software may not act the way you expect it to. If you take away one thing here, it should be that secrets are the keys to your kingdom. So it's imperative to handle them properly. Among other things, you should be able to answer questions like where they are, where they end up, how they're accessed, how they're updated, how they're revoked, who can use them, when they use them, how they use them, and what happens in a compromise. But the conundrum is that while secrets are extremely sensitive, they must be accessible to you and your application. And in your day-to-day, accessibility will often feel like a more pressing concern. It's convenient, but it's dangerous. On that note, let's break down some common practices you may use in your day-to-day. If you have keys to the kingdom, how do you handle them? Maybe you don't. After all, your code and scripts probably need secrets to do their work, interact with other applications or tools in the tool chain, and access cloud resources. So the happy path may be to simply hardcode your secrets in plain text. But that means anyone who has access to your application can read and probably edit them. And if you check them into a version control system like GitHub, anyone anywhere can read them. That's regardless of whether your secrets are in your application code or a distinct file. If they're in a configuration file, well, you may be violating a separation of concerns, and you still may check the file in by accident. A secrets file dedicated to holding your secrets is no more foolproof. It may sound like a simple mistake to avoid, but data leaks via GitHub are actually pretty common. In 2019, researchers scanned nearly 13% of GitHub's public repositories and found that over 100,000 of them contain exposed secrets, and thousands more are leaking new, unique secrets every day. They also noted that it wasn't just inexperienced developers leaking secrets in hobby projects. Several large, prominent organizations were too, including a popular website used by millions of college applicants in the US and a major government agency in Europe, both exposing their respective AWS credentials. Maybe you set your secrets in the environment instead then. Heroku's 12-factor methodology for building SaaS applications made popular the practice of storing configuration in environment variables. And since secrets are often spoken about in the context of configuration, it may follow to store your secrets in environment variables too. Heroku actually recommends doing so with credentials to external services such as AWS S3 and Twitter. If you have a Node.js application, you probably store your secrets like that in environment variables via a .m file like you see here. And it's not illogical to do so. A primary reason is that your environment configuration file is separate from code, so the environment variables are easy to change between deploys without touching code and less likely to be checked into a version control system by accident. There are many downsides of storing secrets in plain and simple environment variables, though. To keep it short, they're leaky and susceptible to misuse. If you use an environment configuration file, anyone who has access to your application can still read and probably edit your secrets like in any other code or file. On top of that, the environment is implicitly available to your entire process, so it's nearly impossible to track how your environment variables may be accessed or exposed. For example, they're commonly logged or printed in plain text for debugging and error reporting. And since environment variables are passed to children processes, your secrets are made available to anything your application calls, including third-party tools. Then maybe you encrypt your secrets first. That's a good start. But while encrypting secrets protects them from immediate threat, it isn't a complete solution. For starters, rotating or updating secrets is critical for your application security. But whether you store your encrypted secrets in a dedicated file or in environment variables, they're awkward and error-prone to change at regular intervals and functionally impossible to change between deployment. In addition, you now have an encryption key that unlocks the encrypted secrets. But that encryption key is a secret in itself. So how do you secure it without kicking the can down the road? This is a challenge we'll revisit later in the presentation. Already, we can see problems with the common ways you may handle secrets in your day-to-day. There's a lot that can go wrong when other developers, bad actors or third-party applications have access to secrets that you didn't intend for. For one, your secrets become susceptible to misuse. At best, it may be hard for a developer or third party to grasp the sensitive nature of secrets they're not supposed to have access to in the first place. Their implicit expectation will probably be that there's nothing special about these things they can freely access, but that doesn't align with the requirements you may have for tightly controlled access surrounding them. And that can result in something like an entire database being deleted, as with the DigitalOcean example. When secrets aren't overlooked, they're still awkward and error-prone to manually configure, manage, and rotate. And since you don't really know or can control things like where your secrets ends up or who's accessed them, they're not trivial to revoke in a compromise. All too often, though, secrets are misunderstood and mishandled. As a result, it's pretty difficult to maintain them properly. But it's sort of a chicken and egg problem. Is it difficult to handle your secrets because you lack visibility and control over them? Or do you lack that visibility and control because you haven't handled them properly in the first place? And these problems are only exacerbated when you're working in a team. How do you decide on and maintain access levels that make sense for your team's workflow? You know now about the principle of least privilege, but how do you enforce it? If Charlie needs an API token, but not the database password, how do you split up your environment configuration file and control what he accesses? Or what happens if he's ready to push a new update, but you're on vacation? Even once you figure that out, how do you securely distribute secrets to team members who need them? When you onboard Bob, how do you get his necessary files and credentials to him? Do you send it to him over Slack, email? Or maybe Alice has containerized everything, but still needs a bunch of passwords to work on your machine. Do you just ask her for them? Will she post them somewhere like Basecamp? Then do you store them locally? And if Alice leaves your team, how do you know which secrets she's accessed that you now have to update? Maybe your AWS credentials are a good starting point, but how do you propagate the changes? What's the downtime if you stop your application, find all 10 instances of the credentials in 10 different places, replace them, recompile, and redeploy? You can probably see by now that if you don't have structure, process, and security around your secrets, the problems can and will keep stacking and stacking. While you may feel like it's just a password here or a token there for the sake of ease and convenience, eventually you'll find you end up with a big headache called secret sprawl. Your secrets are sprawled everywhere, or at least they can be sprawled anywhere. They're sprawled across code, configuration, and communication channels. Maybe you're familiar with this yourself. After all, it's so simple to just send a database password or an API token over Slack. Maybe you're more clever than that, though, and you only send half of it over Slack and the other half via email. That way, someone would have to access 2 of your communication channels to get the full secret, right? Maybe you even encrypt the secret first and send the encryption key via a third communication channel, like SMS. And added onto that, you take a screenshot of the encryption key so you can send a photo of it instead of pasting it in plain text. But the encrypted secret and the encryption key, which is yet another secret, are still just sprawled, aren't they? How do you keep track of them, see how they're being accessed, or control how they're being used? And if that's not enough of a headache, secrets are sprawled across your infrastructure too, from CI tools to artifact repositories. This can quickly be made worse as many applications shift towards serverless and/or microservice architectures, and secrets need to be shared in the cloud or between services. In any case, you lose visibility and control over your secrets. You can no longer answer questions like where they are and end up, how they're accessed, updated, and revoked, who can use them when and how, and what happens in a compromise. It may feel more convenient or worthwhile to simply be able to access your secrets from anywhere at any time, especially when you're first starting out or working on a small team. Quite frankly, our team gets it. We've felt the confusion, frustration, and inconvenience around secrets ourselves. But if you want growth and longevity, plus less headache later, you'll thank yourself if you shift your focus to securely handling your secrets now. So with that, I'll hand it over to Adam, who'll share with you how you can do that and existing solutions that can help you do that.
Thanks, Rebecca. So now that we've seen what a secret is and how we get secret sprawl if we're not careful, let's see how we can do better and securely manage our secrets. I'll go over some principles for doing that, as well as some considerations in choosing a system to manage your secrets and some existing solutions that do that. Centralization is critical to secrets management. You need to go from this to this. You need to establish a single source of truth for your secrets and a single way of sharing secrets. When you don't have that, you do weird things to share your secrets, as Rebecca alluded to. But when you do have a centralized system, you don't have to do weird things, and you gain visibility and control over who has what secrets. Previously, Rebecca showed secrets might be sprawled across your infrastructure. They might even be passed down service to service in your pipeline. But after centralization, only your app needs to have its secrets, or rather, whatever service needs secrets will get only the secrets they need, thereby reducing the attack surface area of your application as a whole. To drive it home, let's look at some common work scenarios and contrast what they look like when you have sprawl versus how they're improved with centralization. So let's say we have secrets all over the place and Alice quits. What secrets does Alice have? Does she retain access? We may not know. With a centralized system, it may be straightforward to revoke her access. Now let's say that Bob just joins the team. Without a system in place, he's not likely to get all the secrets that he'll need to do his work in a complete or controlled manner. Instead, he may plug away at his work and then find he needs a credential of some kind and have to ask around. By contrast with the centralized system, we may have our secrets organized by project and be able to give Bob all the access he needs with a few clicks. And secrets won't be a roadblock to him doing his work. Finally, let's say Charlie updates an API token, which will be the most common scenario of these three, which would be updating a secret. So the old token is no good anymore, and applications will crash if they try using the old one. What does Charlie need to update to make sure everyone has the new token? It may be a chore just for Charlie to hunt down the places that need to know, the people that need to know. And by contrast with a centralized system, if he updates it in the one centralized place, the next time any service or person needs that secret, they'll grab it from the same place and automatically get the updated version. We're now ready to discuss secrets managers, which are centralized systems for your secrets. They are systems that help you securely store and manage your secrets and give you visibility and control over them. In the next several slides after this one, I'm going to mention these existing secrets managers to illustrate some particular points. So a few of the players in this space, as you'll see, are EnvKey, Secret Hub, Doppler, and Vault. And with that, let's consider key aspects of a secrets manager. And let's say that you're sold on using a secrets manager. What do you need to look for in one? First, a secrets manager must keep your secrets safe. To do that, it should encrypt your secrets. So the first thing you should ask about a possible solution is, what is its encryption scheme? How does it keep them safe? And second, how does it accommodate having multiple users? How does it let you share access safely? This won't necessarily apply if your project will always be a solo one, but most of the times that you'll reach for secrets manager will be when you're working on multi-person projects. And third, you need to know how to actually use it in your application. How do applications actually get secrets? You might have to significantly adjust your workflow depending on the secrets manager that you pick. In the next few slides, we'll look at each of these three aspects in more detail, and we'll also look at existing secrets managers along the way. And by the way, the mini map in the top right shows we're on the first of the three key aspects we're going through. And to get started with that, let's go over a few encryption best practices. First, you should encrypt client side. This means secrets are encrypted before being transmitted across a network. So secrets never leave your machine unencrypted. That way you don't have to trust the party you're sending it to, nor the communication channel that you use. Still, when it comes to security, it's best to have a multi-layered strategy so that if one layer fails, the system as a whole is still secure. And with that in mind, you should use an encrypted communication channel, which is called encryption in transit. Encryption in transit can include any temporary stopping points between the client and the final destination. Finally, your storage device should also be encrypted. This is called encryption at rest. Something to keep in mind is that not all secrets managers will implement client-side encryption, although encryption in transit and at rest are universal. One of many existing secrets managers is EnvKey, and let's see what they have to say about encryption, taken from their homepage and their security docs. So we never see your secrets in plain text, they say. And apart from providing client-side encryption, EnvKey follows best practices. All data is encrypted in transit and at rest. That's great. And in their security docs, they lay out their security model. And they say, even in the unlikely scenario of a compromise of EnvKey servers, it should not be possible for the attacker to read or modify an organization's secrets. This is just one real-world example of a company that implements client-side encryption, encryption in transit, and encryption at rest. There is another encryption best practice to look for that falls along sort of a different dimension than the ones previously discussed, and that's the idea of key wrapping. The basic idea is to have a two-layer key system, where a key is something that encrypts something else. Secret Hub uses this idea of key wrapping to create individually encrypted secrets. One layer of key is the individual's account public key, a public key for each person that will have access to secrets. And the second layer of their key wrapping scheme is the encrypted secret itself, which is encrypted with the individual's account public key. You can also use this idea of key wrapping in a different way, which Haven ended up doing, and which we will discuss later in this presentation. After you've figured out the encryption scheme a secrets manager uses to keep your secrets safe, you need to know how it lets you safely share access. How can other members of your team get access, and how can applications get access in a way that respects the principle of least privilege? One new player in the secret space is Doppler, and they let you manage access like you see here. At the top left, we see these red box shows access is on a per project basis, and we're looking at a project called Yoda Speak. On the bottom right, we see that access is given on a per environment level, so that you can assign someone to have access in the development environment, staging environment, and/or production environment. So let's say that both the encryption and the ability to safely share and control access seem solid for some solution you're considering. Then you'll want to know, how do I actually use it to provide secrets to my applications? At a high level, either your applications has to fetch the secrets that it needs, so you have to write some application code to do that, or your application is run in a certain context such that it already has the secrets it needs. Let's look at the first way, where the secrets manager is a highly decoupled and passive component. Using a .env file falls into this category. In Node.js applications, you would import a .env module in your application code and then call a method on that module to load the env file. Another approach that falls into this category is storing your secrets in your Git repos, encrypted. Mozilla has an open source tool called SOPs that lets you do this. The downsides with this specific Git-based approach is it doesn't permit fine-grained access control or logs, and it doesn't adhere to separation of concerns, as secrets are much closer to config than code. Finally, you might make an API call within your code to fetch secrets. AWS has a service, maybe we should call it a product, called AWS Secrets Manager, and they provide SDKs to interact with it. A downside of using AWS Secrets Manager alone is that you need to get familiar with AWS, and you have to set all the permission groups and policies yourself. What these approaches all have in common is that you must write application code to fetch secrets. On the other hand, your application might also be run with the secrets it needs already available. For example, if you use an orchestration service such as Puppet or Docker Swarm, there will likely be a built-in way of specifying secrets, which will then be made available in the environment your application code executes in. Another approach that falls in this category is what the Secrets Manager Secret Hub does. Secret Hub actually runs your application as a child process and injects the secrets into the environment of that process. This gives Secret Hub some level of control. You can monitor the standard out and standard error streams of your application, which lets it redact secrets that you might accidentally be logging. This is the approach the Haven team ended up taking, which we will go more in depth in this presentation later. Overall, existing solutions can be broadly categorized as lightweight or heavyweight, where lightweight emphasizes ease of quickly getting started using it, and heavyweight emphasizes features. Even in the lightweight category, there's some diversity. For example, Doppler emphasizes usability and has a growing list of integrations, but arguably EnvKey emphasizes security more, as they use client-side encryption, whereas Doppler doesn't, so that your secrets are sent plain text and you trust Doppler that they securely handle them after that. The heavyweight ones, such as Secret Hub and Vault, tend to offer more features, but at the cost of greater complexity. Vault is far and away the most popular solution for bigger companies, and they do have an open source version too, but Vault is complex. Their own docs even say, and I quote, "Vault is a complex system that has many different pieces. Using Vault means committing to learning a new vocabulary, one that is particular to them. It's a lot of work setting up and maintaining it, so it can be overkill for many teams." Ultimately, all commercial solutions here are third parties that you have to trust. We see a room for Haven, an open source solution that is easy to get started with and has an interactive UI, something simple and usable, but something you have full control over. Other open source solutions exist, but none of them are ideal for getting immediately productive with. Either there's a lot of setup required, or they are really built for a specific use case like Docker. So our team built a new solution that is secure, but also straightforward, and lets you get started in minutes. And now I'll turn it over to my colleague Dan, who will introduce Haven.
Thanks, Adam. Let's take a look at what Haven has to offer. The architecture of a Haven instance can be roughly split up into two components, the client side and the corresponding AWS infrastructure side. On the client side, each user, be it a dev, admin, or application server, uses the Haven application to interact with the instance's secrets. All of these users have Haven installed on their personal machines and are using Haven to interact with the same AWS infrastructure, albeit with varying levels of permissions. In this section, I'm going to predominantly focus in on the client side, and in the next section, my colleague Aram will mainly hone in on the AWS side. How does Haven work? We'll see how you, as a single user, can get Haven set up as an admin and integrate your project with Haven. Then we'll take a look at how you can add another user to Haven to work on your project. And finally, you'll run your app with Haven on a production server. Before we go any further, I want to explore the roles when working with Haven. You could be a Haven Secrets admin or a user with Haven permissions. The first person who needs to get up and running is the admin. This is the person responsible for creating every project, every user, assigning permissions to said users, and reviewing access logs. The admin can also add and update any number of secrets for their project's environments. We'll discuss Haven users in more detail later on. Now, let's run through how you as an admin would get started integrating Haven with your project in order to manage your secrets securely. First, as the admin, you'll need to install the Haven Secrets CLI package from NPM, which comes loaded with our CLI tool. We also offer a UI that you can download separately. You can use either tool to interact with Haven. Both use the same Haven core package behind the scenes, issuing the same commands to AWS, so there's no functional difference between using the UI or CLI. It's all a matter of which workflow you prefer. You will then run Haven setup. This initial setup only happens once. Here, Haven creates your Haven account file, which contains your Haven credentials, and places it in a Haven folder on your personal computer. It also sets up your AWS account to provision the proper Haven resources for creating projects in their environments, adding users, setting permissions, and adding and updating secrets. These credentials authorize you to perform the actions described above. Running setup assigns you as the Haven Secrets admin, which gives you complete control over anything you integrate with Haven. You'll be able to add project secrets to your AWS account through Haven. Now, what does that mean? There's no external Haven server with your secrets. Your AWS account is the single centralized storage. Haven also takes care of the process of ensuring that your secrets are encrypted in transit, as well as when they are stored at rest in your AWS account. In this scenario, since you're working on a solo project, this might not seem like a big deal, but it will come into play later in other scenarios. Now that you have Haven set up on your computer, it's time to start integrating projects with Haven. Here, you have a project called BlueJ. Currently, the secrets are not managed properly, either by being hard-coded, stored in .m file, etc., and it might not seem like any harm, but we can recall from earlier just how easily this can spiral everywhere, leading to secret sprawl. Let's see how you can start using Haven to secure BlueJ's secrets. Since Haven can be used for multiple projects, we need to have Haven provision the proper resources for this project on your AWS account. As the admin, you are the only person who will be able to create and delete projects under this account. It's a good idea to give the projects the same name for the sake of simplicity. When we create a project with Haven, Haven will provision the proper resources for that project, the project's environments, and the groups with predefined access levels. When we create users in the future, we can easily add and remove them from groups to determine their permissions. For example, we can add a developer to the BlueJ's production read group, which will give them access to read any of BlueJ's production secrets. Since you're the admin, you'll have full access to all secrets added to your AWS storage. Next, add all your secrets to whichever environments you wish to include. Haven encrypts every secret and will only decrypt the secret based on the user's permissions. Now that you have Haven set up and have integrated project BlueJ, let's add a new user. Going back to this role comparison, we could see that Haven dev users have a lot less capabilities than the Haven Secrets admin. They will only be able to create, read, and/or update secrets per project environment, depending on their permissions. Creating a user is an admin-only capability. When you create a user, Haven will provision temporary credentials for this user that will be saved to your computer. You'll then send these temporary files to the intended developer. Your developer will also need to install Haven from npm on their personal computer. Here, the developer has received the temporary credentials you sent them and has stored them in a Haven file on their personal computer. Haven users don't need an AWS account since they'll be working as a user in your AWS account with only the permissions you grant them. All the Haven resources have already been set up earlier by you in your AWS account. However, the developer cannot interact with any projects and secrets just yet. They'll first need to run user setup on their computer. This command connects them with your AWS account. Haven uses the temporary credentials to create their official Haven credentials and replaces the temporary ones in their Haven account file stored on their personal computer. Once their official credentials are generated, the temporary ones are deleted and won't be able to fetch the user's official credentials again. Also, to add another layer of security, if these temporary credentials are not used within an hour, they will become void and you, the Haven Secrets admin, will have to generate a new user for this developer. The developer will now be able to interact with Haven by creating, updating, and/or reading secrets based on their permissions. You'll be able to grant them read and/or write access for secrets on a per project environment basis. Granting permissions is an admin-only capability. To see this all at a higher level, let's walk through this example. Earlier, you put some secrets into your central AWS database through Haven. Haven encrypted them in transit and in storage. Then, the developer we just created was able to use Haven on their client side, and since they have read permissions, they can access your organization's central AWS database and decrypt the secret, giving them access to the same secret you added to this centralized storage. Both the admin and the developer are using Haven on their own computers to access the same AWS account set up by you, the Haven Secrets admin. When it's time for your developer to leave your project for whatever reason, you can completely revoke them, or if they're just switching teams, you can revoke them from only certain project environments. We can see that the revoked user can no longer access these secrets in your AWS account. Whenever a user loses permissions, Haven will notify you to rotate the secrets the developer once had access to by flagging them. We've seen how you, as the admin, can get up and running with Haven. We've also seen how to integrate a project with Haven. Then we took a look at how to add other developers to work on your projects. Finally, let's look at how you can add a production server to run your app with Haven. This process is fairly similar to adding a user. As the admin, you're the only person who is able to create and delete servers under this AWS account. Every server you create will be considered a Haven user and will at most be able to create, update, and/or read secrets based on its permissions, but you should limit the access of these servers to only have the read permissions they need for a specific project environment. When you create a server, Haven will provision temporary credentials for this server and save them to your computer. You'll be using these temporary credentials soon, so hold on to it. As the admin, you'll give the server read permissions to a project's desired environment. Next, SSH into the server where your app will be running and install Haven globally or as a dependency in your project. You'll then place the temporary credentials in a Haven folder on this server. Since Haven servers are still considered users, you'll run Haven user setup on this server. This command connects the server with your AWS account that was set up in the previous example. These temporary credentials operate the same as the developer getting set up. This server is ready to run your application with Haven. Using the command haven run followed by the project name and environment and ending with your application's run command, you can run your application. Haven will fetch all the secrets in this project environment, decrypt them, and inject them into your app. Haven also redacts all secrets from standard out and standard error to provide a greater degree of security. Here's a zoomed out picture of everything we've covered. Multiple clients on different machines can use Haven to access their secrets either through the UI, CLI, or in your application. Each client has Haven installed on their personal computers. Every secret, set of permissions, and the master encryption key is stored on your organization's AWS account set up by the Haven Secrets admin. Every developer and every application is using Haven to interact with this single central AWS account. Now, I'm going to throw it over to Aram to show you how Haven manages to achieve all these features under the hood.
Thanks, Dan. Now that we've seen the core functionality of Haven, let's take a deeper look at its design and architecture. Let's revisit the architecture diagram we saw earlier and go over the AWS services we used in the right side of the diagram. We used Identity and Access Management, also known as IAM, to dictate who has permissions to access which secrets and perform which operations, Key Management Services, KMS, to generate a singular master key and perform encryption and decryption, Lambda, which allows a user to run functions as a service on AWS to enforce validity of temporary credentials, DynamoDB, a NoSQL database to store secrets on a per project and environment basis, as well as logs. And we chose to use DynamoDB due to its low latency. And CloudFormation, which allows one to codify AWS infrastructure and easily set up and tear down DynamoDB tables and permissions. Now that we've seen the architecture of Haven, let's take a deeper look at some of its key aspects. First, we'll take a look at the encryption scheme used by Haven. From there, we'll see how Haven handles multiple users and access control. And finally, we will go over how Haven injects secrets into applications. Now, ideally, we want secrets to be encrypted so they are not in plain text. With regards to encryption and secrets, however, a problem arises. Assume you use symmetric encryption, so the encryption key both encrypts and decrypts your secrets. But that encryption key is a secret in of itself, and a particularly sensitive one since it can unlock all of your secrets. You might try to encrypt that key with another key, but that would be yet another key you have to encrypt, and this chain would keep going ad nauseum. One way to solve this problem is to have a trusted third-party service store a master key that you don't have physical access to. Instead, you dictate who has permissions to use it to perform encryption and decryption operations. In the case of Haven, we use the battle-tested AWS key management service to create and store this master key and limit encryption, decryption access to it via AWS IAM policies. We don't need to worry about safely storing this master key since AWS handles that. Now we've decided to use a master key. How is it actually used in practice? You could encrypt your secrets directly with the master key or use the common technique of envelope encryption. This is very similar to the key wrapping technique Adam mentioned earlier. Envelope encryption involves generating a unique data encryption key for each secret and encrypting the secret using that data encryption key. Then the data encryption key is encrypted by the master encryption key. The encrypted data encryption key and encrypted secrets are then stored until they are decrypted later. To decrypt your data, you simply perform this process in reverse, decrypting the data encryption key with the master key, and then using the decrypted data encryption key to decrypt your secret data. There are some advantages to this. First, it's harder to brute force the encrypted data since each is encrypted using a different key. Second, you can store the encrypted data encryption key alongside the data it encrypts, meaning you only have to worry about the security of the master key. Let's take a look at how Haven implements envelope encryption. So Haven utilizes the AWS Encryption SDK, an AWS service that lets you perform encryption and decryption using your KMS master key. First, a unique data encryption key is generated and is used to encrypt the secret on the client side, as seen in the top right there. Then, as shown in the top left, that data encryption key is encrypted using the singular master key stored in KMS. Both of these encrypted pieces of information are encrypted in transit via TLS and sent to DynamoDB to be stored alongside each other as shown in the bottom of the diagram. Thus, we can see that Haven encrypts your data client-side, in transit, and at rest up on DynamoDB. When dealing with a centralized secrets manager, handling multiple users and ensuring the principle of least privilege becomes very important. Haven handles this using IAM permissions. Access to secrets is limited on 3 dimensions: by project, environment, and action, where an action is read-only or read-write. Here in the Haven UI, we are looking at the secrets for the dev environment for Project BlueJay. We can see that the user Sue has read and write access to these secrets. Handling permissions of existing users is straightforward enough, but the creation of new users posed a challenge for us because creating credentials for a Haven user means creating a new secret. Our solution was to create temporary credentials that are only good for 1 hour. Additionally, these credentials don't have permissions to do anything except request permanent credentials. This draws heavy inspiration from temporary password policies that many websites employ, where the temporary password expires after a short time. In our case, an AWS Lambda enforces this 1 hour limit. Taking a look at the flow, first, the Haven admin adds a user either in the UI or CLI. As we saw earlier, a Haven file with temporary credentials is then downloaded and the admin sends this to the new user. Next, the new user places the Haven file in their home directory and runs user setup. Haven invokes the AWS Lambda using the temporary credentials, which in turn checks if it is still valid and updates the Haven file. Finally, the new user tells the Haven admin that they set up their account, and the Haven admin is free to add that new user to projects and environments. After seeing how Haven encrypts secrets and sets up new users, the question becomes, how do you get secrets from Haven into your applications? Any solution should fulfill the following requirements. First and foremost, it must not contribute to secret sprawl. If you're going the distance and using a centralized secrets manager, you don't want to fall back into secret sprawl for that final step of getting secrets to your applications. And second, it should be easy to integrate. The solution shouldn't be a burden that causes developers to not want to use it. Now let's briefly recap some possible techniques for getting secrets to an application that Adam mentioned earlier and some of the problems with them. We could retrieve the secrets from Haven and write them to a .env file to be used by the application. The problem with this approach is that we're back to secret sprawl, since our secrets are sitting in a .env file out on a server in plain text. We could store the encrypted secrets in, say, GitHub or in a .env file and then decrypt those secrets as part of a pre-deploy script, but this approach is a bit more work for the user and also muddles the separation of concerns between code and configuration. Another approach that briefly came to mind was to require the developer to manually fetch the secrets within their code and use them accordingly. We quickly passed on this approach since it requires changes to application code and is not as easy for a user to set up. There was one existing solution that stuck out to us, however, secrets injection. You might recall Adam talking earlier about the technique the Secrets Manager Secret Hub uses. In a nutshell, you store your secrets in Secret Hub and then use Secret Hub to run your application, passing in the command to start your application as an argument. Secret Hub will then fetch your secrets, run your application as a child process, and inject the secrets as environment variables. This technique comes with some key advantages that we can use in Haven. First, your secrets aren't stored on the application server, so you don't need to worry about contributing to secret sprawl. Second, due to the nature of child processes, Haven can redact any secrets leaking out on standard out or standard error. This leakage can often be yet another source of secret sprawl. Finally, it's easy to implement in an application. We can simply install the Haven package and change our application's start command to include Haven run. So let's briefly cover how child process works. A process can be simply thought of as a running program. Many programming languages allow for the creation of subprocesses while running a program. And oftentimes there are several options for how to create that subprocess, but in our case, we will focus on the spawn method from the Node.js child process library. When using the spawn method, you specify the program you want to run, and that program is ran as a child process. The standard I/O of the child process is piped to and from the parent process. That is, standard in is piped into the child from the parent, and standard out and standard error are piped from the child to the parent. This is what allows us to both provide a simple wrapper to fetch secrets and call any arbitrary run command a user might have, as well as let us intercept any logging of secrets on standard out and standard error and redact them. So how does this child process technique fit into our architecture? First, all you need to do is place the Haven file for the application in your home directory and install the Haven CLI npm package as a dependency in your application. Then, as seen in the console, you will use the Haven run command to run your application, specifying the project, environment, and command you want Haven to run. In the example shown here, BlueJ is the project, prod is the environment, and node bluej.js is the command that will be ran by Haven. As shown in the upper middle half of the diagram, Haven will fetch the secrets for the project environment combination and then spawn a child process via the command you passed to Haven using the spawn method from the node child process library. The secrets are injected into this child process as environment variables, making them available for the application. Then, as the application runs, Haven intercepts both standard out and standard error, redacts log secrets, and then logs the redacted results, as we can see in the lower middle half there. Now, there are some features we'd like to eventually add to Haven. First, more runtimes besides Node.js for the child process we inject secrets into. Second, per secret access control to allow more granularity. Third, some direct plugins and integrations with credential providers. And lastly, email and notification systems to permit greater control. And with that, this is the team that brought you Haven. Thank you for coming to our presentation, and we'll give it a couple minutes for any questions you might have. So feel free to ask away. So it looks like we have a question here from Rodney. What made you guys choose encryption as your area of study? So kind of while searching for a topic, there was a lot of stuff that was on the table, but there was a Hacker News article about secrets management that sort of caught our attention, and that's sort of what kind of led to us digging deeper to the section.
Just to add on to that, I'd also say encryption is just a part of this whole secrets management thing. As we were building this, and in previous projects in Capstone 2, we found that secrets management really was a problem and a pain point that we experienced. So it was great to explore that area further.
Okay, I guess we got one here from Senna about how do you establish trust for your code for end users for this type of software? So this is open source, and it is all hosted on their AWS, so they're free to check through our code, take a look at all of it, and that's sort of how that's resolved, I guess.
I'm seeing that we have a question from Daniel. Were there any techniques or methods you considered around encryption before you settled on the solution you used? And that was interesting because one thing that we all saw mentioned was this concept of end-to-end encryption. If you use the Signal app, you may have even noticed that they say they give you end-to-end encryption. As we dug into that, we found that it's kind of a loose term, more of a marketing speak, that essentially means client-side encryption or encrypting on your side before it goes anywhere else, although there are varying definitions for that. So we thought we wanted to do end-to-end encryption. We decided to get more concrete and that just sort of abandoned that idea. And another interesting thing that we looked into with encryption was the idea of encrypting a different secret for every user. And I'm trying to recall what the challenges would have been with that. Ultimately, we decided that it wasn't worth the much greater complexity for doing that. If it comes back to me, I'll let you know.
Just adding on to that, I guess with end-to-end encryption, we were getting pretty close to that. And I remember I was stressed for a period of time where I really wanted to make that happen. But beyond the client-side encryption, encryption in transit, and encryption at rest, the thing that kind of distinguished end-to-end encryption from all of that is that, like, for whatever reason, if we really had to decrypt those secrets, well, the master key is stored in AWS, so AWS could technically go in there and decrypt the secrets, which prevents it from being end-to-end. So we did consider some solutions around that, such as encrypting the secrets on the client side using the client's public key and having them keep their own private key, but then that would have just added too much complexity on the user side.
So we have one here that I think we can all sort of address. It's about how our Capstone group had 4 as opposed to 3. And can you talk about how that's both an asset and liability and for our team dynamics? I guess One thing I would say is with 4 people, you do sort of run into where even a small decision sometimes turns into kind of a big conversation. A lot of time is used trying to come to a consensus among 4 instead of just kind of taking the immediate best idea and just sort of going from there. I don't know if anyone else wants to follow up on that.
Of course, some assets are, we can split the work. Once we are all comfortable with the architecture and our plans to move forward, we could really delegate, one person to a different corner and work a little faster that way.
Next question, Austin said, you mentioned early in the presentation that you want the admin who must manage the secrets to be able to go on vacation / take a break. Did you find a solution for a service that should necessarily be so centralized and still allow some flexibility for admins? So that point was earlier in the presentation when we were addressing the problem of secret sprawl and you not having that kind of visibility and control over your secrets, where they are and who can access them, which makes it a lot more difficult when you're in a team setting. So if you're the admin and you are the person controlling these secrets and you go away on vacation or you want to take a break, it's more so how do you control access levels or distribute these secrets to other team members? But with a centralized secrets manager such as Haven, that problem is addressed because you'll have such access controls and actual access levels built in already.
And to add on to Rebecca's answer, in our research, we noticed that Vault was popular for big teams, but you really need, as an organization, to have the bandwidth to manage that. So we're more targeting smaller teams who wouldn't have a multiplicity of admins necessarily.
Yeah, and also just the last part of that question, a solution that's centralized and allows that flexibility, I would say that it's actually that centralization that allows for such flexibility, because otherwise it would be the hassle and overhead of how do you get, sorry, these notifications are going off right now. How do you get these secrets that aren't centralized to someone in a secure manner?
We have a question from Justin. Was there any bottlenecks you identified in your system and how do you address them? So I guess one bottleneck sort of is with the storage you decide to use for your secrets. Up on AWS, there's plenty of different services. They've dozens and dozens of services up there, and there's several storage ones. And since if you're injecting these secrets at runtime, you don't want to be the bottleneck for retrieving these secrets. So DynamoDB has very low latency. So that's why we ended up going with them for our storage solution. We also have a couple here that are what was the most challenging problem you had to deal with for the project and kind of how we had to deal with it as a team. There's a lot of, I guess, trying to figure out the way we were going to handle encryption with AWS and also all these services. Just figuring out what services to use. So there was I guess, a lot of research looking into that. And I mean, a lot of the project was just a lot of research before you kind of start coding it up and prototyping. And just, like I'd mentioned before, there's dozens of AWS services. So looking through and going, okay, we can use this one for this, but what trade-offs come with that? And sort of just figuring out how to put all these together in a cohesive unit. Well, I don't see any more coming on through here. So thank you again for coming out to our presentation, and good rest of your day. Thank you.